talking SHA weakness and password cracking. One thing I want to say before I start with the talk is this is my first presentation at all. This is my first security conference at all. This is not my native language. And yeah, to be honest, this is the first time I'm visiting a university also. And yeah. Everything that can go wrong will go wrong, and I hope I can compensate that with the information inside my slides. And yeah, I think I will just start with that. You heard it before from Per. My name is Jens Stoiber. I think you know me as Phantom, which is my nickname. I'm the author of the Hashcat and also the Hashcat user. Before I started coding Hashcat and also Hashcat, I was doing a lot of security research. That is searching for exploitable security holes in open source software and non-open source software. And no, I did not sell them. And I did not exploit it or did not use it to make money out of them. I reported them, I fixed them, I worked together with developers. And if you want to see something of that work, just take a look at the bug track or the video security advisory. My current work status is I'm a programmer, I'm a coder. But this job is not crypto or security relevant. Everything I do here is my personal interest. My employer has nothing to do with Hashcat. He knows about Hashcat, but he has nothing to do with this, and everything I show you here was made in my free time. I found this weakness, SHA weakness, around 2 years ago. But I decided not to release it at this time because SHA 3 was not voted at this time. So in case a developer which uses SHA 1 inside his application decided to change or will decide to change SHA now to SHA 3, he has the chance to do that. The first thing we should know about SHA 1 is that it's processed sequentially. It's very important to know that because by doing this, the algorithm makes it possible to hash any size of data. So it can be very small, like a password, or it can be very big, like a file. And it's doing this by splitting the data into 512-bit blocks. These 512-bit blocks are represented in the code, in the actual code, in the real implementation, 16 32-bit words, 16 times 32, 512. This is our password. Inside this array is our password. For each 32-bit word, 4 characters of the passwords are stored. That means in the first element of that array, the first 4 characters of the password located there. The input data, which is our password, is expanded by another 2048 bits of data. And this expanded data is generated out of the input data, out of our password itself. We call this phase word expansion. Yesterday we heard from John, he called it message expansion, and in the SHA 1 RFC it's called key expansion. So I really don't know what is the real word, a real name for that. I will call it word expansion. Maybe it's wrong, then correct me please. Both input data and expanded data is used with the 80 steps of SHA 1. Which is something you maybe don't know. SHA 1 consists of 80 steps of SHA 1 functions, and but I will not go into this because the weakness is not inside the functions, it's inside the word expansion. And so we will not focus on them. And yeah, here's a little table that shows how many instructions are required to calculate one transformation of SHA1. The instruction count is another way of showing how long it takes to calculate one of these blocks. And it's a very generic solution. So if you have different hardware, the instruction count may change. But this instruction count I show you here is from a hardware that is the fastest I know of the instructions count that are possible. The T column stands for the position inside the 80 steps of SHA1. And the word expansion file, as you can see here, starts at position 16 and goes up to 80. That is 64 steps. The word extension is a phase of SHA1 transformation, as the function calls is a phase of transformation of the SHA1 transformation, and its purpose is to generate a bigger volume of data from the input data. So I'm not really sure why they're doing this, but one thing I can say about this, if you do it, it's harder to reverse that algorithm from the last step to the first step backwards. Because to do this, you need to know the last position, the input data at the last position. So you can reverse it at this point, but you have to do the word expansion at least to know the data at the position 80 in this case. So as I said before, this is where the weakness is located in SHA1. The input data is a simple function, as you can see here. Input data is mixed up using this function for 64 steps. So we have the first 16 32-bit words, which is our password, and then there is 64 steps adding up, so we end up with 80 steps. And by doing this, we have 2048 bits added. This is an unrolled view of that word expansion. It's a C, but I think it's easy to explain. If you take a look back, this is the WT is our function. T is in this case something that is iterated from started from 16 and goes up to 80. And for each step, you can see the W. This is the array where our password is located in. Is increased by 1. So this is the reference implementation from SHA1. So how can we exploit this? And this is the most important part, I think, here. The first thing you need to do is that the password candidate generator. This is one part of the password cracking tool. Needs to hold the data between W1 and W15 constant, fixed. This is done in what I call the outer loop. We store the information of that pre-computed W16 to W80 in the pre-computed buffer PW. Then, inside the loop, you can change W0. That means you can change the first 4 characters of your password. Since the word extension uses XOR, we can apply the W0 to the pre-computed buffer afterwards, because it cannot overflow. If we use XOR, we just flip bits around. No information is lost. And that's the thing. If it would use add instead of XOR, information could have been lost. I think that's the reason why SHA 256 and 512 is using add in the word expansion instead of XOR. When iterating is finished, we can step to the next W1, which is the 5th position of your password, or any later W value. And then you can continue this as long as the key space holds. This is how the arrow view looks with my optimization in this case. And you can see here the crossed out W0 in the first line. This is because in the auto loop, we do not know W0, but we still calculate PW16 by purpose, even if we know that the value is not correct. For PW17, it's no problem because W0 is not part of it. The same is true for 18, 20, 21, etc. 19 is a different case because PW19 contains the information PW16, and PW16 depends on W0. So we cannot know the correct value for PW19 at this point. What we have to do now in the inner is that we have to correct these invalid buffers. We pre-compute 20 steps of rotates from W0 because we will use them afterwards. And when we've done this, we apply them to the pre-computed buffer. As you can see here in W16 again in the crossed outline, this is the reference implementation. And the right side after the equal sign, this is how my optimization looks like. And you can see here the first time how I was able to replace 3 XOR operations and a rotate operation with just 1 XOR operation. And W17 can be still, the thing is for W17 we can still assign PW17 because, as you know from before, it does not contain information from W0, so we simply assign it and that's it. We saved all 4 operations. Yeah, this is a view a little bit later in the loop to the 18 steps, because here you see something that is a bit problematic. The farther you get, the farther your step is inside SHA1, the more XOR instructions are required to correct the value for each W value which is used inside the SHA function. So the farther you get, the slower the process is. Starting with W33, you can see with the red mark, it requires 6 XOR operations instead of 4. So this optimization is actually slower than the reference implementation at this position. And if you take at the right side, there's a table. W75 requires 4,703 XOR operations to correct the buffer for W74. So this is not really helpful. But there's something you should know about XOR. XORing a value to itself results in 0. That's the one thing. And if you ever written some assembler program, one of the first things you learn is if you want to set a value to 0, a register to 0, that you can XOR it with itself and it will result in 0. And another thing is that every value XORing with 0 is the value itself. So the conclusion is we can ignore as many XOR operations. That means, for example, 4,703 XOR operations from before, if the number of the W value which is correct is even. And this is one of my favorite slides for this. Looks a bit complicated, but it is not. The first block, the top block, is the reference implementation. The block below is how it would like with my optimization. And the right block is how my optimization will look like in ball 9. So if you take a look at the first XOR operation after assigning PW41, you see W04 is XORed with W04. And as we know, subvalue XOR, subvalue results in null and 0. So the same for the third and the fourth value. So we have 0, 0, 0, 0, XOR 0, 0, and this goes down straight to 6. In other words, the value for W41 is the same value as PW1, our pre-computed buffer. It's exactly the same value, whatever W0 was. Even W0 is part of that buffer. And here's another optimization. Simple optimization. You see the same block. The red one is exactly the same code, so we can pre-compute it once, and we replace 3 operations with 1 operation. And this is how this looks from a final view. Left side is the reference implementation, right side is the optimized implementation. And you see a lot of XOR functions on the left side, and a very few XOR operations on the right side. The instruction count from the optimized version of SHA1 is this. It's around 880 instructions for the fastest hardware now to calculate this transform. And there's another optimization which is already known. This is the early step out at position 75. This is after you have reversed 1 step of E, the auto loop. And this makes it faster. This is a known optimization to 828. And with my optimization, this goes down to 694. 694 is a lot, because that means this is 21% faster than the reference implementation. The files for download, sorry Per, I think I'm a bit too fast. Files for download, this URL, it's currently locked. I will unlock it in the next 10 minutes. It contains this presentation, the XOR 0 generator, so you do not have to do this by hand. And all the results from the slides that did not fit in this because the screen was too small. Yeah, that's it. Questions?
The rotation, are they really pre-computed, or do you compute them when they are needed?
I pre-computed everything in the first steps of the inner loop. You mean that? The rotates, the variables?
Yes.
Yeah, I do that, but the compiler is optimizing that. So I do it in the source code in the first position, but the compiler is optimizing it.
More questions? You on?
I was going to say it's very clear as well. So.
Yeah? Then you guys have to explain it to me afterwards. Yeah, Jeremy?
So if you're, to leverage this, do you have to change sort of the order that you're going to feed your word list?
Yeah, you can. The thing is, you have to ensure that starting with W1, the value does not change. So if you pre-order the dictionary in memory, you can do it.